This program is brought to you by Stanford University. Please visit us at stanford.edu.
Has anybody done the homework and found the operator for circular polarization? No. What is it? Yeah. Right. Let's just do it quickly. So I'll come back to you. Since we assigned it homework, let's just do it quickly. Before.
Was there a eigenvalue associated with those eigenvalues?
Sure.
Yeah, what were they?
1 and minus 1.
Oh, 1 minus.
Right? Right. Okay, let me just write the other two cases. There was the there was the what do we call it? The observable for the polarization when the polarization was in the vertical and horizontal directions, plus for horizontal, minus for vertical, and we call that P. Why don't people throw these away when they're no good anymore? I don't. Let's try this. Ooh, that's cool. Okay, there was the observable representing polarization in the vertical and horizontal plane, plus for horizontal, minus for vertical, and we call that, oh boy, 1 minus 1, 0, 0. The X polarization state we labeled as 1, 0. The Y polarization, the vertical polarization, we labeled as 0, 1. Okay, so this is the object which has eigenvectors x and y with eigenvalue plus 1 and minus 1. Then there was the polarization, the observable for the 45-degree case. We called the states theta, and we represented that by cosine theta, sine theta, and then there was the orthogonal one, which was theta plus pi over 2, and that had a column vector which I think was sine of theta and minus cosine theta, I think, if I remember. Yeah, that'll work. This one is orthogonal to this one, sine times cosine minus cosine times sine. That'll do it. Well, okay, we're going to talk about whether that matters or not. Okay, I guess we wrote it this way last time. It doesn't matter, in fact. And this was 1, 1, 0, 0. Sorry, that was for the special case, of 45 degrees, and we called that 45 degrees 1 over root 2, 1 over root 2. And this one would be 1 over root 2 minus 1 over root 2. This would be this and this. And finally, we discussed circular polarization. We've started to discuss it. The two states of circular polarization, again, you can think of them as two distinct orthogonal states. Orthogonal means physically distinguishable in a single experiment. And I guess I called that, I put a little rotation notation like that. This would be positively polarized lights, positively polarized circular polarization. And the wave function for that, or the 1 over square root of 2, and you can take it to be 1i. Here's the first place where complex numbers come in, and the opposite polarization, same 1 over square root of 2, 1 minus I. These are, yes, these are again orthogonal. You can check that. Remember when you check it that you should complex conjugate one of them when you take the inner product, and then multiply the upper components and add it to what you get when you multiply the lower components. All right, what is the observable? It goes with circular polarization. That, I don't remember what I called it. Did it have a name? I guess we can just put a little rotation symbol, and that, as was mentioned a moment ago, is minus I, 0, 0. We can check that this observable, when it acts on the polarization state, on the circularly polarized states, these are eigenvectors with eigenvalue +1 and -1, and that you can check for yourselves. It's very straightforward. The hardest part of it is remembering that I squared is -1. All right, now, where are we, and what are we doing relative to what we did the first day when we studied classical mechanics? The first day when we studied classical mechanics, what we discussed was the possible states of a very simple system with a discrete number of states. The discrete number of states could have been 2 for a coin flip, 6 for a die, or any number, and we just then said the state of a system is a point in a set of states, however many we have. And we also discussed the evolution of the system in terms of arrows, which took you from one state to the next, to the next, to the next, in discrete time steps. Right? Thus far, how far have we gotten by comparison with this? Well, we've gotten to the point where we've described what a state is. We've gotten to the point which is about the analog of the place where we would be when I would say that a state is just a point among a set of points, where the set of points represents the space of states. Now, the space of states is a vector space. Well, we've gone a little bit beyond that. We have also discussed observables. What would observables be in classical physics? Observables would simply be numbers which would label these states. Functions, for example, we could assign this state over here, the observable value, some observable. Let's call it k again. Now it wouldn't be a linear operator. We would just call it k. Here's a good example of an observable. The head coin flip. We could assign heads 1, and we could assign tails -1. What about the die? Well, the die already comes equipped with a numerical observable, 1, 2, 3, 4, 5, and 6. Of course, nothing would prevent us from relabeling so that 6 became 1, 5 became 4, and mix them up in some funny way. But an observable then would just be an assignment of a number to each state, basically. When the system moves around from one point in the state space to another point, the observable changes. So when we flip the head and tail back and forth, the coin heads to tails to heads to tails, we get a sequence of observable values, 1, -1, 1, -1, 1, -1. We can imagine moving the die around in some deterministic way, and again, it would sweep out a series of values of the observable. There might be several observables, several different possible things that we could, numerical values we could assign. Okay, classical mechanics, of course, is similar. The state space simply becomes a continuous version of the same thing, labeled by a set of coordinates and momenta, labeled by a set of p's and q's. So the state space is still a set, but it's a continuous set labeled by q's and p's, q's being coordinates, p being momenta. A multi-dimensional space. Again, a state is a point in that space. And again, observables are functions of momentum and position. Momenta and positions. For example, one observable might be p itself, the momentum. That would just be a function which is just p. It takes on different values at different heights. Another observable would just be q. P plus q is an observable. All of them would be functions of points on here. Quantum mechanics, extremely different. How far have we gotten? We've gotten about as far with quantum mechanics as I have just described in approximately, what was it, 4 minutes? 4 minutes in the classical context. We've described what states are. They are vectors in a vector space. I actually have not even been complete about that yet. And we've described what observables are. They're Hermitian operators. And it took us several weeks to get to that point. But now that we've gotten to that point, we have some equipment now, some tools to go on and discuss the next sorts of things, which are how systems move. Well, I'm not quite ready for that yet because I do want to review a little bit and to do a little bit of mathematical formalism, which we haven't discussed yet. First of all, let me remind you what you do with states when you have them. States are vectors. They're the bra vectors and ket vectors. And there are two physically interesting things that you can do. Let us suppose you know the state of a system and you're interested in some observable. Well, one thing you can do is to compute the average value of the observable, the thing that most physicists call the expectation value. Let's call the observable again just k for, well, yeah, k is fine. Sometimes I remember to put the little hat on top of it, sometimes I don't. The average of it is just to sandwich k between the state, the ket version of the state, and the bra version of the state. That's the average. And it would be something which would be useful if you were going to measure k, if you were going to prepare the system in the same state over and over again, and many, many measurements of k, and take the average. It would be a useful thing to do. And it's a physically interesting quantity. Another thing is, supposing we have two states. Supposing we have A and B. And as it happens, A and B are eigenvectors of two different observables. Let's say that A is an eigenvector of k with eigenvalue, let's call it alpha times A. And let's suppose that B happens to be an eigenvector of a totally different observable, L, which happens to have eigenvalue beta times B. There are two eigenvectors, but of different operators. Then the interesting quantity that we've discussed over and over again, although I may not have spelled it out in quite this detail, is we could ask, what's the probability that if we prepare a system with a definite value of the observable k, namely alpha, we do something to the system so as to make k definite, and namely with the value of alpha, then what's the probability that if we then measure L, that we get beta? What's the probability that if we measure L, we get the answer beta, given that we prepare the system with a definite value of k, namely equal to alpha? The answer is the inner product of A with B squared. Or another way to write it is times its complex conjugate, which we can write as B times A. That's equal to two things, in fact. We can call it the probability AB. It's the probability, again, that if we prepare the state with alpha and then measure L, that we get beta, but it also happens to be the probability that if we prepare the state with L equals beta and then measure K, that we get alpha. Was that clear? Well, it hardly matters since you get the same answer. Oh, did I write it wrong? You're right, I did. Right. This one is the complex conjugate of this. Now, these are the two kinds of questions that you ask in quantum mechanics. Average values for an ensemble of many experiments, and again, probabilities, which again only make sense for many repeated experiments. Both of these have the feature that the answers are insensitive to a certain operation that you can do on any one of the vectors in the space. And the operation is called multiplying the vector by a phase. Oh, before I go on, let me just remind you of one thing, that physical state vectors always should be normalized to make the total probability equal to 1. That's one rule. So we can think of physical state vectors as unit vectors. Simply, that's the statement that the sums of the squares of the coefficients, when you expand the state in a basis, those should add up to 1. All right, but let's discuss another operation that you can do. You can take a state, or the whole state, not a piece of it individually when you add up pieces, but the whole state, the whole vector, and you can multiply it by a phase. And I'm going to explain what that means in a moment. But the point is, it doesn't make any difference whatever to the physical properties of the state. All right, so what does a phase mean? A phase is a complex number. Let's just remember very quickly, for those who haven't been using complex numbers for the last 50 years. A complex number is an x and a y with an x equal to iy. It also can be represented as an r and a theta. And it can be represented in the form x plus iy. X plus iy, that's the complex number z. It can also be written in the form r cosine theta, that's x, plus I r sine theta, that's y. And another way of expressing it, which is just more or less notation, is to write it as r times e to the I theta. E to the I theta is just another way of writing cosine theta plus I sine theta. Very quickly, when you multiply two complex numbers, you multiply their r's and you add their angles. So if we had two complex numbers, let's call one of them r e to the I theta. The other one, let's call it, what's another letter that's near r? No. Yes. R1 and theta 1, theta 1. And another complex number, r2, e to the I theta 2. Adding them is easy in this form. We just add the components. Multiplying them is easy in this form. When you multiply two complex numbers, the result is r1, r2. You multiply the lengths, and then you add the angles, e to the I theta 1 plus theta 2. Okay. One more point, the notion of complex conjugate. The complex conjugate of a complex number is just the corresponding complex number in the lower half plane, which has exactly the same form r, except instead of e to the I theta, it has e to the minus I theta. So whatever z is, r e to the I theta, z star is r e to the minus I theta. Now, in particular, there are special numbers, which are called just pure phases, special complex numbers, for which r is equal to 1. They are the numbers which lie on the unit circle. The numbers which lie on the unit circle, in other words, for which r is equal to 1, and theta can vary around from 0 to 2 pi, those numbers are called phases. Well, actually, usually, the language is a little bit ambiguous. Sometimes the angle is called the phase, And sometimes any number which is of the form e to the I times an angle is called a phase. All right, so e to the I theta is a special kind of number which I will call a phase, even though sometimes the phase is reserved for the angle there. And it has the property that when you multiply it by its complex conjugate, let's call this z. If we multiply z times z star, and if z is a pure phase, then the result is just 1. Why is that? Because it's e to the I theta times e to the minus I theta. And when you multiply complex numbers, you just add the phases, and e to the 0 is just 1. All right, so this is a special class of numbers which are characterized by z times z star equal 1. Good. Now, what does that have to do with these vectors? Formally, or just mathematically, we distinguish two vectors. Let's call one of them A, and let's call the other e to the I theta times A, where theta is any angle, a number. Right? This is a vector, this is a number times a vector. Formally speaking, they're two different vectors, just as a vector and twice the vector are two different vectors. So mathematically speaking, this vector is not equal to this vector. But all of the physical properties of these two are identical. How to see that? Let's go back to the various things that we might do with, well, the various physical questions we might ask. For example, supposing we took psi here. Let's take the case of the expectation value or the average value of any observable at all. Doesn't matter what k is. Supposing we multiply psi by e to the I theta. If we multiply psi by e to the I theta, what happens? In other words, if we multiply the ket by e to the I theta, what happens to the corresponding bra? Right, the corresponding bra is psi e to the minus I theta. So what would happen if in this sandwich, in this K sandwich, we replaced the bread, psi, by e to the I theta times psi? Well, this, the bra vector, sorry, the ket vector would pick up the factor e to the I theta. This would get the factor e to the I theta. This one would get the factor e to the minus I theta. Now remembering that e to the I theta is just a number. It's not an interesting operator of any kind. E to the I theta times e to the minus I theta is just 1, and this would just cancel out of the expression. So there would be no change in the expectation value of any operator if we replaced any vector, any one of them, the vector which happens to describe the system in particular, if we multiply it by a phase. So in that sense, the phase is irrelevant. We can choose the overall phase of the state any way we like. Doesn't make any difference to what we would measure. Likewise, in the probability, if we multiplied either A or B or both by a phase, it would also cancel out because, let's suppose we multiply B by a phase. The ket vector over here would get multiplied by a phase. The bra vector over here would get multiplied by the opposite phase, and they would cancel. You could do the same thing with A. So again, you see that there is no physical significance to the phase of the wave function. The norm of the wave function should be set equal to 1, and the phase of the wave function is completely irrelevant. Okay, let's come back for a moment to polarization. Polarization of photons. I said, for example, that the vector x is equal to 1, 0, and the vector y is equal to 0, 1. Nothing would have stopped me from replacing y by a new version of itself, namely 0, minus 1. Minus 1, multiplying by minus 1 is multiplying by a phase. E to the I pi is equal to minus 1. So a special case of multiplying a state by a phase is just to multiply the whole state by minus 1. I could have done it with x also. It doesn't matter. All of these are physically... This is physically identical to minus 1, 0. It is also physically identical. I shouldn't put equals. They're not equals as vectors. What kind of symbol can I use? Let's, two squigglies means approximately equal to. Not even approximately equal to. A dot over the equals. Okay, a dot over the equals, which means has the same physical significance as. Because that means something else. We'll take the dot over the equals to mean has the same physical significance as. All right? Putting a minus 1, but also we could also multiply it by any phase. E to the I theta, 0. All, no, sorry, dot. They all have the same physical meaning as a state in which the polarization lies in the horizontal direction. Same thing with the polarization lying in the vertical direction. We can multiply by minus 1 or anything else. 0, e to the I theta. Yeah, I love them, but I'm not sure they're quite right. So I will use the term has the same physical significance as. I know it's a lot of words, but
Well, similar is literally multiplying by a factor.
all right, for you I'll use similar. Is similar to. All right. Similar is something that has to do with triangles, I thought. But anyway, let's move on.
Kind of shape preserving. Kind of shape preserving.
I don't know. It just has the same expectation values and probabilities, that's all. All right, so we can come back to here now, to these circular polarizations. I could change the definition of the circular polarization. For example, I might multiply by I. Supposing I took the positively circularly polarized state and changed its definition by multiplying both top and bottom by I, then this would become similar to, in Mike's terminology, similar to one over square root of 2. Now I'm going to multiply everything by I. I is a pure phase. It's e to the I pi over 2. 1 over square root of 2, I minus 1. I times 1 is I times I is minus 1. So this has exactly the same physical content as this one here. In this particular case, we can count parameters. We can now count how many parameters it takes to describe the polarization of a physical photon, the physical polarization state of a photon. Let's count. All right, we can start with a general vector. Let's call it alpha beta. That's 2 complex parameters, 4 real numbers altogether. So a general vector in the vector space has 4 real parameters associated with it. Now, first of all, there is one combination that we set and we freeze, namely alpha star alpha plus beta star beta is equal to 1. That's the condition that the sum of the probabilities add up to 1. So we started with 4 real parameters, one equation among them. How many are left? 3. Okay, so there's 3 parameters left over. Three parameters left over. But now there is one more fact. If we multiply by a phase, it doesn't change the content of the state. That means the overall phase doesn't have any content. There's no content in the overall phase. Equivalently, I can always take the upper entry to be real. I can always multiply by the appropriate phase. You have to multiply the top and the bottom by the same phase. But we can always choose, for example, this would be arbitrary, but we could always choose to make the upper component real by multiplying by the appropriate phase to get rid of the complex part of alpha here. So we could always choose alpha to be real. Now that it's real, let's give it another name, A. I'll use Latin letters for the moment for real numbers and complex numbers down here, beta. All right, so how many do I have left? Let's first of all solve this relationship here. We have to have that the sums of the squares, we have to have that a squared plus beta star beta equals 1. There's an easy way to solve that. We just write that beta star beta is 1 minus a squared. And now we can write that beta is equal to the square root of 1 minus a squared times any phase, e to the I theta. If beta star times beta is a number, that means that beta is the square root of that number times a phase. General fact follows from the definition of beta star and beta. All right, so we can now write that the most general possibility is a real number up here. Again, I choose a real number arbitrarily here. Then to make sure that it's normalized, I put 1 minus a squared square root down here, but then I still have the freedom to put in a phase, e to the I theta. How many overall parameters are there? 2. 1 real parameter here and 1 real parameter for theta. So that means there's a 2-parameter family, of polarization states for a single photon. What are those 2 parameters? Physically, why are there 2 parameters associated with the polarization of a photon? So let's come back to an electromagnetic wave. The simplest electromagnetic wave is a wave which is polarized, whose electric field is along a particular axis. All right, so the wave is going into the blackboard. Its polarization is along some axis which we label theta, plane polarization. That's only 1 parameter. Incidentally, it's not the same as this theta here. That's only 1 parameter. That polarization could lie along any direction, but if it's a plane polarized wave, it then there's a 1-parameter family of them, corresponding simply to the direction of the electric field, the direction of the electric field theta. Now, if I combine 2 waves with 2 different polarizations, and the electric fields are in phase with each other, for example, they're both cosines, then if the electric fields are in phase with each other, it just gives you a polarization in a different direction. But if the 2 directions of polarization are out of phase with respect to each other, then the electric field can sweep out a circle, but it can also sweep out an ellipse. For example, here's a wave that sweeps out an ellipse. The x component of the electric field is equal to cosine of x minus ct. And if I take Ey equal to sine of x minus ct, then if I stand, let's say, at x equals 0 and watch what's happening, the electric field moves on a circle. That's circularly polarized light. All right? But if I take EY to be 1/2 of that, now the electric field in the y direction only grows to half the size of its maximum in the x direction. I don't think I drew that well. That becomes elliptical polarization. It's elliptical polarization, but it's described by a major and minor axis, the major axis in this case being along the x-axis. We can consider rotated versions of that. We can imagine combining electric fields together in such a way as to create elliptical polarization along an arbitrary axis. In other words, with the major axis being along any axis, that's one variable, the angle of the major axis, and the other variable being the eccentricity of the ellipse, the ratio, the aspect ratio of the small diameter to the large diameter. That is the other parameter. So there are two parameters describing the polarization. One is the angle of the major axis, and the other is the eccentricity of the ellipse. Two real parameters. Now, there are some special cases. When the eccentricity goes to 0, it becomes plane. Eccentricity goes to 0 means it collapses to an infinitely thin ellipse. Then it becomes plane polarized. In the limit that the eccentricity goes, I suppose you would say to 1, then it becomes circularly polarized. And in that situation, theta doesn't matter anymore. For a perfect circularly polarized photon, there's no special axis for the major axis. But in general, in the generic situation, two real parameters to describe the polarization of a photon. And so it's not so surprising that we found two real parameters describing the state of a photon. Somehow these two real parameters are in one-to-one correspondence. Some functions of them are the eccentricity of the ellipse and the rotational axis of the ellipse. Not the rotational axis, the long axis of the ellipse. I'm not going to tell you how to... Shall I tell you how to find out which is which? Okay, I'll tell you what you can do. Yeah.
Two parameters, but there's also positive and negative rotation.
Say again.
There's also the positive and negative rotation. So the polarization, it still corresponds to two.
Actually, yeah. Okay, good. All right. So there's one parameter which corresponds to the eccentricity of the ellipse. It starts at circular polarization and it starts to squash down, and it goes to 0. If you go past 0, just go right past 0, then the polarization changes. The polarization goes in the other direction. In other words, if this is rotating this way, and we squeeze it and squeeze it and squeeze it until the lower part of the ellipse passes the upper part of the ellipse, then it rotates the other way. So the two parameters are enough to describe both polarizations. When some number goes negative, it describes the other polarization. Yeah, right. You can think of it as negative eccentricity. Right. Right. But supposing, for example, I wanted to find the direction of the major axis. Well, here's what I suspect. I could ask the question, what is the probability that if I measure the linear polarization along an axis theta, that I'll get +1 or -1? All right? So let me first ask, given this circular polarization here, and in fact, I better change the name of this angle here. I'm going to call it phi. All right? Now, let's take a linear polarized photon, or let's take a state of linear polarization. As this one here, that was described by cosine theta, sine theta. And now let's ask, supposing we start with this photon And instead of measuring the circular polarization or the elliptical polarization, let's measure the linear polarization along the axis theta. That means put a polarizer, a linear polarizer along the direction theta, and see what the probability that you go through is. What's the probability that it's polarized along the theta axis? Well, it's just the inner product of the state of the photon with the eigenstate describing a particular polarization squared. So the probability that this photon is that this elliptically polarized photon is measured along the theta axis. If I were to measure the plane polarization, what is that going to be? It's going to be the inner product of this with this squared. Let's write down that inner product. It's cosine theta times A. Let's call this, let's see, we call this theta. And this psi. Okay, so what is psi theta? Inner product of psi with theta. Psi with theta, it's A times cosine theta plus square root of 1 minus a squared e to the I theta, no, e to the I phi times sine theta. Do I have it right?
Doesn't one of them have to be conjugated? So either minus I theta or
Yeah. One of them should be conjugated. Good. E to the minus I theta, e to the minus I phi. This is not yet the probability. Let's compute the probability. We multiply this by its complex conjugate. Do we really want to carry this out? I don't really want to carry it out, but I want to tell you what you do with it when you find it. When you find it, you will then know the probability that this particular photon is polarized along the theta axis. Now, how do we find the major axis associated with psi? We maximize the probability with respect to theta. We look for the direction theta, which maximizes the probability that this photon lies along this direction. So what we would do is to multiply this by its complex conjugate. That's too hard for me. I don't feel like doing that. Do I feel like doing it? No, definitely not. Multiply this by its complex conjugate. Homework assignment. Multiply this by its complex conjugate. Think of phi as fixed. Phi is the fixed parameter associated with this photon, and we're going to adjust this axis until we maximize, until we have the best fit, until the linear polarization maximizes the probability, maximizes the overlap with this elliptical polarization here, maximizes the inner product or the square of the inner product. That will tell you what the major axis of psi is. It's more or less intuitively clear that whatever the major axis of psi is, in other words, if it corresponds to a elliptical polarization in this direction, and then we measure the linear polarization in different directions, that the probability will be maximized when the linear polarization matches the diameter of the major diameter of the ellipse. All right, so you think of phi as fixed, square this, and maximize it with respect to theta. In other words, differentiate with respect to theta and find the place where it's maximum. That will tell you the angle of the major axis. The eccentricity, you can okay, the eccentricity would have to do with the difference of the probability that the photon lied along that direction or along that direction. In other words, if you find that there's a very high probability that this elliptic photon is polarized along some linear direction, that will mean the eccentricity is small, and the difference between the two probabilities is some measure of the asymmetry of the ellipse. I didn't really mean to get into this. I just really only wanted to point out to you that there are two parameters that govern the physics of a particular state vector, and that those two parameters are in one-to-one correspondence with the two parameters associated with the angle and eccentricity of the ellipse. Yeah.
So it seems like then ascent counterclockwise or clockwise is missing.
Say it again.
Well, you have two parameters. You have
Yeah.
the orientation and eccentricity. So what seems to be missing is ascent, whether it's clockwise.
Okay, well, somebody just asked me that, and I thought I answered it, but let me go through it again. The eccentricity is a parameter which can be negative or positive. You start with an ellipse which looks like this, which is rotating in this direction here. Well, let's start with a circle. Circularly polarized is not eccentric at all. Goes in this direction. Let's draw an axis in there. Doesn't matter which axis, any axis in there. And now start changing the eccentricity by squeezing the ellipse. We squeeze the ellipse and it goes down to here. All right. Now, eccentricity, you would think, ends at the point where it's linearly polarized. At that point, the eccentricity goes to 0. I think it's counted as 0. Right? The eccentricity becomes 0 when it collapses to a line. But you can keep going. You can make the eccentricity negative. When it goes negative, these two pass each other. The upper branch here, which is moving from the bottom to the top, becomes the lower branch, and the lower branch becomes the upper branch. So the point is, the real parameter, as you vary the two real parameters here over their entire range, positive and negative, you pick up both senses of polarization as well as angle and, okay? Good. All right, now our next step is to understand how the states change with time. That's the big next step. How do they change with time? The analog, oops, no. The analog of the classical question, if we start with a space of states, which is just a bunch of points, how do you move from one to the next? Now, with just a set of discrete points, you would have to imagine a kind of stroboscopic time evolution where you would divide time into little intervals, and at each instant, or at each interval, make a jump from one state to the next. There would be no way to do this continuously. In quantum mechanics, you can have a finite dimensional vector space. For example, just the two directions of polarization, but you can have continuous time evolution. And the continuous time evolution goes through the fact that you have sort of continuous interpolations between states. You have not only 1, 0 and 0, 1, but you have continuous interpolations between them. For example, the polarization vector could rotate with time. That would not be circular polarization. The linear polarization could rotate with time. That's a possible motion of the polarization of a photon with time. And although anytime you measure the polarization along the axis, you only get one of two answers, as if it were a coin plus or minus, nevertheless, the time evolution of it can be completely continuous and does not require that you think stroboscopically. So quantum mechanics can have discreteness of possibilities and still have evolution which is continuous. The question is, how do we describe the evolution of quantum systems? Now, let's go back for a moment to the evolution of classical systems. When a classical system evolves, it's just a permutation of the states. The relationship between states stays the same. Now, there's only one relationship between states in classical physics. Well, states I now mean this discrete system, heads and tails or dice or whatever, some finite number of states. Right? That's all there are. There's just a finite number of states. There's only one relationship between them that makes any sense. They're either the same state or they're different. That's the only relationship between them. They're the same or they're different. If they're different, we call them different. If they're the same, we call them the same. One of the features of classical physics is a conservation law that says that with time, different states will maintain their differences. In other words, it will not happen that two different states, let's call it A over here and B over here, will both evolve to C. If they both evolve to C, then you would lose the distinction between the starting point. If they both went to C, for example, if our rule of evolution for dice was that 5 goes to 3 and 2 goes to 3, and then a whole bunch of other ones here, then if we arrived at 3, we wouldn't know if we came from 5 or 2. That's not allowed in classical physics. Evolution, which sort of loses distinctions. So if two states start different and they evolve with time, they stay different. Right? That's the basic conservation of relationships between states. The corresponding thing in quantum mechanics is very, very similar. The relationship between states is maintained with time. What is the relationship between two states? Right? You can say they're different or they're the same. So supposing I have two states, let's call them A and B again. Of course, what it means for them to be the same is that A equals B. They are the same vector. What does it mean for them to be different? Well, now we have to decide exactly what we mean. Yeah, we could put dot here. Fine. We could put dot there. It would mean that they are equal up to a phase. We could use a stronger form of equal, but then remember that, that we're not really interested in distinctions which are only distinctions of phase. But we could put the dot there if we like. But what is the concept of two states being different? Well, it could just be A equals not B. But you could have two vectors, for example, two polarization states, one which is polarized horizontally and one which is polarized almost horizontally. If we were to take that photon which was polarized almost horizontally and measure its horizontal polarization, we might in fact discover that it was horizontally polarized. In other words, it might go through the horizontal polarizer. There's only one state which is absolutely forbidden from going through that horizontal polarizer, and for which we could definitively say that the photon was different than the horizontally polarized photon. And it's the vertically polarized photon. The vertically polarized photon will not go through the polarizer. So we could say that the vertically polarized photon is orthogonal to the horizontally polarized photon. The orthogonality relationship is the relationship which is the analog of classically different, measurably different than a single experiment, that you can tell with one experiment that it is one thing and not the other. So that's the relationship that we would like to express, the relationship of different, and that relationship is that BA is equal to 0. Or BA is equal to 1, which would say they were the same. More generally, the relationship between two states is the overlap between them. It tells you how similar they are. Right? If there's an overlap between states, it means that there's a finite probability that if you choose to measure one thing, you'll get, you know what the point is. If AB is not equal to 0, but for example, close to 1, then the two states are quite a bit alike, and if you measure some observable which would distinguish them, well, they simply won't be well distinguished. So the important relationship between states is inner product. If it's 0, they're different. If it's 1, they're the same. If it's 1, they're the same. Remember that they are normalized states. The only way that the inner product can be 1 is if they're the same. All right? Or the inner product can be 0, in which case they're orthogonal, or it can be anything in between. This is the basic relationship between states, the inner product between them. Now, just as in classical mechanics, distinctions or relationships between states are maintained with time. States which are different stay different as time evolves. In quantum mechanics, the basic rule is as a system evolves, the inner product between its states stays fixed. In other words, as time goes on, let's suppose we start a system with state A, another identical system we start with B. A and B have an inner product between them, and we let them run with time. A runs to A prime. B runs to B prime. After a certain amount of time, the state vector changes. In precise analogy with the way the state might move around in the space of states in classical reasoning. A goes to A prime. A prime need not be orthogonal to A. It'll just go to something else, A prime. And at the same time, B, if we started the system with B, it would go to B prime. The basic conservation of information idea, the basic conservation of distinctions or relationships between states simply says that the inner product of B prime with A prime is the same as the inner product of B with A. In other words, for example, if A and B are the same state, then after they evolve, A prime and B prime will be the same. If A and B are orthogonal, and you run them for a while, then the result will remain orthogonal. That's the basic assumption of time evolution in quantum mechanics, that the relationships between states stays fixed with time. Now, can we derive that? No, I don't think we can derive it. It's an observed fact, but it comes together with a lot of connections with things that you do know, such as energy conservation. So for the moment, let's just take it as a given that relationships between states are maintained with time, and try to figure out what that means. Yeah?
You said that if you measure the vertical photon going to a horizontal polarizer it gets 0, and therefore you know that it's different. But how do you know that that just wasn't a 45-degree photon that just happened to return 0 at that time?
Oh, you don't. You don't know. The point is that if you have made a photon which is horizontal, and you then send it to a vertical polarizer, you know with certainty that it will be bounced back. Every time you do it, you can make a whole bunch of horizontally polarized photons. Every one of them won't get through.
Okay, and then one other related question. We're looking at uncertainty principle. If you create a horizontal photon that's, or uncertainty principle, I don't think it would be difficult to create a horizontal photon that's back and horizontal, but won't go through a vertical polarizer. It seems always a small, finite possibility of going through the uncertainty principle. Of being exact.
Well, the uncertainty principle doesn't say that there's any necessary uncertainty in the direction of polarization of a photon. The direction of polarization of a photon is just one thing. It usually takes two things to define an uncertainty relation. But you can polarize a photon as accurately as you like if you can hold your polarizer still enough and your polarizer is perfectly aligned. So there's no restriction on fixing the polarization along a given axis. What you can't do is have the polarization be known along two different axes. There's no state in which the photon is known to be able to go through a polarization in this direction and in this direction. So it's an uncertainty between polarizations in different directions, not an uncertainty in your ability to polarize a photon along a given axis. All right, so in order to implement this idea, let's just discuss it a little bit more. Roughly speaking, what it says, if we don't worry too much about the complex aspects of complex vector spaces, and we just think of ordinary vector spaces, let's say in 3 dimensions, then we can imagine that with time, the state vector of a system, this could represent the state vector of a system, it moves with time. It moves around with time, just so that the system evolves. Properties of the system change with time. But it evolves in such a way that if two states are orthogonal to each other to begin with, they stay orthogonal to each other. Right? It's a kind of rotation of the space of states which keeps angles fixed. Angles between vectors stay fixed. That's the assumption here, that angles between vectors in the space of states stay fixed and don't vary with time, although the vectors themselves may vary with time. So that's the idea that we want to implement. To implement it, we need some more mathematics. We need the mathematics of unitary operators. And we haven't discussed that yet, so when we come back from a 5-minute break, we'll discuss a little more about Hermitian, and then unitary operators. Unitary operators are the operators which preserve relationships between vectors. So let's take a break for 5 minutes. Okay, let's get started. Now, we need to get some mathematical concepts. So some of this is a little bit repeat, but let's go through it anyway. Let's suppose we have a linear operator which is defined to act on the vector space of Ketz. Thus far, we have really defined linear operators. Let's call it L, a linear operator. Put a little hat on it to indicate that it's a linear operator. And it's defined through its action on Ket vectors. So given an A, the linear operator acts on it to give another vector, which I've called C. Now, you may wonder what happened to B. Well, B will come back, but for the moment, let's just call this C. Every A, you can act on it, and it will give you some C. That's a linear operator. Well, that's an operation. The fact that it's linear entails certain conditions, that it acts on the sum of vectors to give back sums, and so forth and so on. I won't go through that again. But given a linear operator, which is defined in terms of its action on Ketz, we can also define its action on bra vectors in the following way. I wish to define, now this is definition, but it's obviously a neat definition. I wish to define the operation of L on a bra vector B. Right. So L acts on B, and it gives us some new bra vector. That's the assumption. When L acts on B, it gives a new bra vector. How am I going to find that bra vector? Let's put in here a basis of vectors and sum over n. According to the principle that when you sum over n, that you get the identity, sum on n of nn is the identity operator, I haven't done anything. This is L on B. Okay? But now I can define this object over here, this object over here, in the obvious way. Let L act to the right on a Ket vector. We know how L acts on every Ket vector. That's implicit in the definition of a linear operator, that we know how it acts on any Ket vector. So instead of allowing L to act on the bra vector to the left, interpret the symbol as L acting on the ket vector to the right and then taking the inner product with B. We can define this matrix element. It's called a matrix element. It's a sandwich, in this case with two different kinds of bread, N and B, with the bologna in between being the linear operator L. And we define it, even though we're imagining that L is acting to the left, let's nevertheless define a single symbol by defining this, by defining L acts to the right on N, and then we take the inner product with B. That gives us a definition of L acting on a bra vector. No, not yet. No, not particularly. L is not Hermitian, or can be Hermitian, but it's not. But it's not necessarily. Let's see. Have I assumed associativity? I always assume associativity. Yeah, that's right. Yeah, that's right. We've assumed. Now this is definition, if you like. This is definition, but it's clearly a neat definition, which will allow us to do all sorts of manipulations in a sort of mechanical way without thinking very hard. That's the purpose of a good notation, to not have to think very hard when you use it and to use it by inspection. All right, so this is the definition. The answer is a bra vector. These are numbers. These are all numbers, and they multiply bra vectors n. And so the result is a bra vector. And this then defines for us how the same operator, which was defined to act to the right on ket vectors, acts to the left on bra vectors. Okay. So linear operators can act either way, either to the left or to the right. And the notation has purposefully been made so that if we have a sandwich, I'm giving up on this one. If we have a sandwich, B, L hat, A, we can interpret this in one of two ways. The inner product of B with, let's put a big bracket around it, using now the associativity, L hat acting on A, or as L hat acting to the left on B, and then inner product with A. That's the point of this particular construction. It doesn't matter whether we think of L hat acting on A and then inner product with B, or L hat acting on B and then inner product with A. Let's define the Hermitian conjugate of an operator A, L. Supposing L is some linear operator such that when it acts on any vector A, it gives us a vector that I'll call C. Okay? This is a correspondence. It's a mapping of vectors into vectors. Right? Starting with an A, you get a C, and L is thought of as a mapping. There's a corresponding mapping which maps bra vectors. Some operator, if L maps A to C, ket vectors, then there's some object, which I'm going to call L dagger, or the Hermitian conjugate of L, which acts the same way except among bra vectors. So if there's a correspondence between every ket vector and a bra vector, then I can also look for a correspondence between operators, so that given an operator L, which takes A to C, there must be some other operator which acts to the left on bra vectors, which induces a kind of parallel mapping among the bra vectors, which is the image of the mapping among the ket vectors. Okay. What's the connection between L dagger, this is also an operator, What's the connection between this operator and this operator? They're not the same necessarily. In fact, they're kind of complex conjugates of each other. This dagger here, which is called Hermitian conjugate, is a kind of complex conjugation. It's not just simple conjugation, it's a little more than that. But since the bra vector A is the complex conjugate of the ket vector A, and the bra vector C is the complex conjugate of the ket vector C, you wouldn't be too far off if you were to say somehow this Hermitian conjugation is representing some form of complex conjugation. And in fact, it is. Let's see if we can find the relationship between L and L dagger. To do that, let's take the inner product of the top equation with B. So here's our equation. Now we're going to come over to here, take the inner product B L hat A. And what is that? That's B C. I've just taken some arbitrary vector B, any vector B, and sandwiched or taken the inner product of both sides of this equation with B. Now let's take the inner product of this equation, not with the bra vector B, but with the ket vector B. That says that A L hat dagger, there's too many symbols. I really don't need that hat, do I? There's really not much lost if I were to leave the hats off the operators, but let's leave them. B. I've now taken the inner product of this side with the ket vector B, and that's equal to CB. Now what's the connection between the two right-hand sides here? They're complex conjugates of each other. If I take the inner product of two vectors, but then I take them in the opposite order, invert bra to ket and ket to bra, then these are complex conjugates of each other. So these two are complex conjugates, and it follows that these two are complex conjugates. So now we can write down one of the connections between an operator and its Hermitian conjugate. And here it is right here, that every matrix element of the original operator, L, is related to the or is equal to the complex conjugate of the Hermitian conjugate, but with the bras and the kets interchanged. In other words, to go from an operator to its Hermitian conjugate, you interchange bras and kets and you complex conjugate. Now, let's consider a useful way to define complex conjugation now. We can define it in terms of a basis. Supposing we have a basis of vectors, and we consider the inner products N, L, conjugate M. If we know all of these, if we know all of the matrix elements in a basis, and we can call these things L, N, M. If we know all of these matrix elements, then we know everything there is to know about the operator. Yeah?
Are you assuming finite dimension?
For the moment, let's assume finite dimension. Yeah. I am assuming finite dimension, but everything I say also applies to the infinite dimensional case. So you can think of taking the limit where the dimension of the vector space gets very, very big. Okay. What's that?
Do you want a dagger on the right side?
Thank you. I do. Right. That is equal to, this is yet to be defined, or this is we assume that we know the matrix elements of L, but this is equal to the complex conjugate of the matrix element of L with the bras and the kets interchanged and complex conjugated. That's what this says over here. Interchange, bras and kets, and complex conjugate. All right? So we now know that, okay, so we can now write an equation. that, well, this of course is equal to LMN. So here's the rule. If you have an operator represented as a matrix, LMN.
Wait, star is LMN star?
Yes. Thank you. Right. All right, so if you have an operator LMN, and what you want is the matrix elements of the conjugate operator, the Hermitian conjugate, LNM, then all you do is take the original operator, interchange rows and columns, which is the same as interchanging bras and kets, and complex conjugate. In terms of matrices, what this means is that if you have a matrix L11, L12, L13, dot, 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 L21, L22, L23, dot, 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 L31, L32, L33, dot, dot, dot. This is the matrix representing the operator L. Then the matrix representing the operator L dagger, Hermitian conjugate, you interchange bras and kets. That's the same as interchanging rows and columns, and it's also the same as reflecting the matrix about the diagonal. Interchange L12 with L21. Interchange L31 with L13. That's reflecting it, and at the same time, complex conjugate. So the matrix elements of L dagger are L11 conjugate. But instead of putting L12 conjugate, we'll put L21 conjugate, L31 conjugate. And down here, L21 conjugate, L22 conjugate, L23 conjugate. So notice what I've done. I've interchanged the rows and the columns and complex conjugated. I didn't do it right? I didn't do it right. Yep. 1, 2, 2, 2, and what's next? 3, 2. Thank you. Right. So take each one of these, interchange rows and columns, and complex conjugate, and that's the Hermitian conjugate operator. It can be thought of as a kind of complex conjugation, but notice that it also involves this inversion of rows and columns. Inverting rows and columns is called transposing. So transpose and complex conjugate combine together to form Hermitian conjugate. Easy idea, not very hard. Now, the class of operators which are their own Hermitian conjugates are the Hermitian operators. So the Hermitian operators are the ones, the special ones, which satisfy L is equal to L dagger. In terms of matrix elements, first of all, it says that the diagonal matrix elements must be real. It says that L11 must equal L11 star. All right, so on the diagonal, if this is to be equal to this, if L is to be equal to L Hermitian conjugate, then it says L11 equals L11 star. Well, that just says that L11 is real. Likewise for L22, and so forth. So the diagonal elements of a Hermitian matrix are all real. Lii is real. And then, as far as the off-diagonal elements, as far as the off-diagonal elements go, they have the property that if you reflect about the diagonal, the element is replaced by its complex conjugate. So Hermitian operators, this is L21 star. L22 is real. L13 should be L31 star, so that's L13 star. This is L23 star, and so forth. L33 is real. All right, so the rule for a Hermitian operator is that the diagonal elements are real, and the off-diagonal elements the images, the mirror images, are complex conjugates of each other. That's a Hermitian operator. Hermitian operators, remember, I'll just remind you, Hermitian operators have the property that their expectation values are real, their eigenvalues are real, and their eigenvectors are mutually orthogonal for different values of the eigenvalue. All right, we've gone through that before. Hermitian operators are the ones which correspond to observables.
In practice, how big of a matrix is one minute?
Well, it depends on how many independent states of a system there are.
I understood, but I'm saying in things that are commonly studied.
Well, again, it depends on what we're studying. If we isolate out as an interesting system just the polarization of a photon and don't worry about anything else, the 2 by 2 matrices. If we want to study a whole photon, then they become infinite dimensional matrices because we have to take into account either the position or the momentum of the photon, which can have any value. So in most real quantum mechanical systems, in fact, in any real quantum mechanical system, they're really infinite matrices. All right? But infinite matrices are hard to write on the blackboard. They're a little bit easy but tedious, yeah. And it's always the case that, or almost always the case, that in practice we approximate the system by a finite number of states to actually do calculations. Not always, but in most cases we approximate by finite dimensional matrices. Okay, so for example, a particle moving on a line where the particle can be anywhere. Well, we can approximate that by a particle which can exist anywhere in some very, very dense collection of positions. Well, still, we have an infinite number of points going between minus infinity and plus infinity. Nothing too bad happens if instead of going out to infinity, we go out to Brooklyn in this direction and in Hong Kong in this direction and just make it very big. And so we work with very, very large, numerically very, very large matrices as an approximation to the infinite dimensional case.
Is analytical reduction of states analogous to this?
Analytic reduction of states, I don't know what it means.
Okay.
Good, so we have the idea of Hermitian matrices, and these are the things which define or which are connected with observables. Real eigenvalues, real expectation values, and orthogonal, mutually orthogonal eigenvectors. They are not the things that we identify with transformations of the vector space that preserve relations. Remember, our goal now is to find the operations which, where are they, which preserve relationships between vectors. I don't know, I erased it off the blackboard. So these are not the operations which correspond to the preservers of relations. Let's try to define those. Oh, incidentally, let's just check first of all that our polarization observables are Hermitian. We had 3 of them. We had one which was 1, -1, 0, 0. All right. The only rule is, for them to be Hermitian, is that the on-diagonal elements should be real, and the off-diagonal elements, when reflected, should be complex conjugates of each other. This obviously has this property, real, on-diagonal, and the off-diagonals are, in fact, complex conjugates of each other, 0 being its own complex conjugate. All right, then we had another one, which was 0, 1, 1, 0. This was, and again, on-diagonal elements real, 0 is real, off-diagonal elements complex conjugates of each other. And the last one, which was P for circular polarization, that was -I, 0, 0. On-diagonal real, off-diagonal complex conjugates of each other. Okay? So these three are Hermitian and satisfy the rules of being observables. Okay, now we come to unitary operators. Unitary operators are the ones which preserve relationships. So let's define what that means. Yes?
Is an observable always Hermitian?
Yes.
Is that a postulate? Or?
Yes. Yes. Yes, but it makes good sense. The things that you actually observe and measure are always real numbers. The objects whose expectation values are always real for every vector, that's another way to define the Hermitians. It's equivalent that if you take any pair of any vector, psi, L psi, if for any psi this is real, then it follows that L is Hermitian. Now I haven't proved that, but it's a couple of lines. It really is very fast to prove that if L is Hermitian, then psi L psi is real, and vice versa. That's a fast, a simple theorem. So the reality of the expectation value, which makes good sense for a observable, and also the reality of the eigenvalues, which are the possible values that you can measure, those are the key signature of things that you actually observe in the laboratory.
I have a question. Does the eigenvectors of the operator have to span the vector space?
The eigenvectors of a Hermitian operator span the vector space. That is not generally true of non-Hermitian operators. It can be true, but it is not necessarily true.
But I mean, so an observable has to have a
Complete set of mutually orthogonal eigenvectors. Right. Now, you can have a complete set of eigenvectors which aren't orthogonal to each other. That can happen, and then the operator would not be Hermitian. Or it could fail to have a complete set of
I can
eigenvectors.
envision an operator that doesn't span.
What's that?
I can envision an operator that doesn't span the vector.
Yeah, you can have, there are operators that don't have any eigenvectors. You know. Oh, definitely not. It certainly would not be Hermitian, since every Hermitian operator has a complete set of eigenvectors. A complete orthonormal, an equivalent definition of Hermitian is that it has a complete orthonormal collection of eigenvectors with real eigenvalues. Right, that's an equivalent definition. All right, but now we're interested not in observables, but in transformations of the vector space. The transformations could correspond to a number of things. They could define the way the system evolves with time, how vectors transform into other vectors under time evolution. It could correspond to symmetries. What are the vectors, for example, here's an example. Given a polarization vector, given a polarization state, theta, we can imagine symmetry operations which rotate the plane of the polarization. We could say, supposing we're interested now in an operation which rotates the polarization vector by a certain angle, that is also a transformation on the space of states. Just the rotation of the polarization vector. There's all kinds of transformations we could do. And we're interested in those transformations which preserve the relationships between the vectors. So let's see if we can't get a handle on that idea. Take any two vectors in the vector space, A and B. Our favorite two vectors again, A and B. Let's take their inner product, AB. In some sense, that defines the relationship between the two vectors. The degree to which they're similar or not similar. 0, they're orthogonal, they're as dissimilar as possible. 1, and they're equal, as similar as possible. Now, let's imagine a transformation which can act on any vector. Let's call it U. U stands for unitary, but for the moment we don't even know what that means. Such that U on A is equal to A prime. For every A, there's an A prime obtained by acting with some linear operator called U. All right? Of course, I don't know why I wrote A here. I think I should have written B. B prime. B prime, B and B prime are just labels. They could run over any vector in the vector space. All right. Now, the same operation has an image among the bra vectors. Remember, if an operation takes place among the ket vectors, the image of it involves the Hermitian conjugate. So, if this is true, then the same operation, except when interpreted in terms of bra vectors, will involve U dagger. All right, so let me write this correctly. Supposing U takes B to B prime, and supposing U takes A to A prime, what does U do, or what, excuse me, then it follows that A U dagger is equal to bra vector A prime. That's the definition of the Hermitian conjugate. If U on A equals A prime, then U dagger on bra vector A equals bra vector A prime. Okay. Now let's consider the relationship between AB and A prime B prime, and let's require them to be equal. In other words, whatever U does, it doesn't disturb the relationship between vectors. It hits A and gives A prime. It hits B and gives B prime, but it doesn't disturb the relationship, meaning that the inner product of the outputs is the same as the inner product of the inputs. So what does that say? Let's just write it down. Substituting for A prime, U dagger A, this is equal to A U dagger, that's A prime, but then B prime is U times B. Okay, simply stated, B prime has been replaced by U times B, A prime has been replaced by U dagger times A. But this should be true. Let's get rid of the intermediate step here. Let's get rid of this. Here is what we require of the transformation U. If U preserves relationships, then for any pair of vectors A and B, A U dagger U B should be equal to AB. But if a thing like this is true for any pair of vectors, if for any vectors, any A and B, sticking an operator in between them does nothing at all, then it follows, this is a theorem, that U dagger U must be the identity operator. If you have some operator that when you sandwich it between any two vectors gives you back the inner product without the operator, then that operator is the unit operator. That's a theorem. That's easy to prove, again, that if A U dagger U times B is equal to AB, not just for one particular pair of vectors, but for any vectors in the vector space, then it follows that U dagger U is the identity operator. It does not say that U is the identity operator. It says U dagger times U is the identity operator. Okay. In other words, U dagger undoes whatever U does. Whatever U does, if you multiply it by U dagger, it undoes it. That says that U dagger is the inverse of U. U dagger times U is 1. Says that U dagger is the inverse operator of U. Another way to write the same thing is that U dagger is the inverse of U, meaning just the operator that undoes whatever U does. Operators with this property, that U dagger times U, the identity operator, those are called unitary. They are not themselves identity operators. They can shift the vectors around, but they shift them around in a way which preserves the relationships. Right? That's the unitary operators. All operators which preserve relationships are unitary. So, yeah.
Are you using relationships in any broader sense than just preserving the product?
That's all I mean by it. Mathematically, that's what I mean by it. Physically, of course, it means it preserves the, if you like, we can call this, the square of this, we can call it the probability that if B, then A. I'm choosing shorthand for something much more complicated. If B, then A, that the relationship is preserved, for example, with time, if U represents the time evolution of a system. So, okay, so this is the class of unitary operators. U dagger U is equal to 1. We have only a couple of minutes, so I'm going to tell you now some of the properties of unitary operators, which, some of which we will prove, some of which you can find in books, and some of which are obvious. First of all, in fact, I'm just going to tell you the properties. I'm not going to justify them right now. Unitary operators have one feature in common with Hermitian operators. They also have complete orthonormal sets of eigenvectors. All right. So there's a complete there exists for each unitary a complete basis n such that U on n gives an eigenvalue lambda n times n. But the eigenvalues are definitely not real. Or they can be real, but in general, they're certainly not, in general, real numbers. The lambdas do have a special property. Let's see if we can figure out what that property is. If U has a complete set of eigenvectors, what can we say about the eigenvalues? So let's use the fact, let's see. I think we'll quit at this point. Let's just quit. Let's stop now. And next week, we will consider the properties of unitaries. And then we're going to go into the issue of Hamiltonians and how systems change with time. Systems change with time by unitary transformation. That's the message. The unitary operators are the things which take you from one time step to another. And I think we've had enough. I've had enough for tonight.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.